So the first thing I actually wanted to do today is we had a couple leftover proofs by contradictions. Okay, but so we had two ones left. I know this is still from chapter 3, but we had two examples left. I want to go back now that your brain is ready to think about, you've done this, okay, and it's had a while to sit in. So let's do a couple of examples to keep those ideas flowing. Okay, so the last two examples from chapter 3. So among any set of 16 days chosen from the calendar, at least 3 of those days will fall on the same day of the week. Okay. So 16 different days implies, at least 3 on same day. So there's our hypothesis, there's our conclusion. We're going to use a proof by contradiction. Okay. So just, when you use anything other than direct proof, you usually need to alert your reader, so let's go ahead and alert them. We use a proof by contradiction. Okay, so remember, in a proof by contradiction, we're going to start by asserting that our hypothesis is true. Okay. So we assume that 16 different days are chosen from the calendar. Okay, our assumption there really is that there are 16 different days. They're not like 3 of them aren't the same day. Okay, so there are 16 different dates. Okay, and then, so we assert that our hypothesis is true, and then we explore and say, well, what would happen if our conclusion were false? Okay, right? So that's what we want to do. We say, all right, well, suppose that, okay, well, what's the opposite, the opposite of at least 3 are on the same day? Less than 3, so at most 2, right? So suppose that at most 2 of the days fall on the same day of the week. Okay, so that means we can have, at most 2 on Monday, at most 2 on Tuesday, that kind of thing. All right, so you've got 16 different days, and the maximum that you can have that share any day is 2. Okay, so what's the least number of days that could cover? You've got 16 days, and there's 2 here, 2 here, 2 here, 2 here. How many days is that going to have to cover? That would be 16 different days, but I'm going to try to minimize the number of days that I can cover. I'm going to put as most on each day as I can. Okay, I can have at most 2 days on the same day of the week.
7?
So, but I've got 16 days.
I'm a bit confused. Sorry.
So if I've got 16 days, okay, let's write this out. All right, I've got day 1. Okay, I can have at most 2 of them there. So I'm going to put date 1 there and date 2 there. All right, that's the maximum. I've maxed that out. So I have to go to day 2. I'll put number 3 and 4 there. That's the maximum that are possible. I'll go to day 3. I can put day 5 and day 6 there. I go to a 4th day. I can put day 7 and day 8 there. I go to day 5. I can put 9 and 10 there. Okay, I go to day 6. I can put day 11 and 12 there. I can't have more than 2, right? So I go to day 7. I put a day 13 and day 14 there. I still have 2 more days. Okay, so I go to day 8 and I put day 15 and day 16 there. Okay, so if I can have at most 2 on any day of the week, then at least how many days must be in a week? There must be 8 days in a week. Okay. Okay. This means that there must be at least 8 days in a week. Okay. Now maybe if you're a Beatles fan, okay, but okay, you should feel like this is a contradiction, right? Okay, so this contradicts the fact that there are 7 days in a week. Okay. And so I said, all right, well, let's imagine that my conclusion was false. Let's follow that path out and see what would happen. I get to a place where it leads me to a contradiction. Okay, so that couldn't have been false. Okay, because that leads me, so it must actually be true. All right, therefore, okay, there are at least 3 days that fall on the same day of the week. Okay. Yes.
Are we going to need to know on quizzes or exams which kind of proof to use, or will you say use contrapositive, use contradiction?
On the quiz, I will probably tell you. On the exam, I might not tell you. Yeah. Okay.
But will it be like painstakingly obvious?
I hope that it will be painstakingly obvious. Yeah. And if it's not, then you might not have studied enough. Yeah. Okay. So, like if you look at the examples, you can see like if there's conclusion, like because of the way it's written, it's difficult. But if you negate it, it's pretty easy. Then you know, all right, probably I want to use, a proof by contrapositive, or so. It will probably be obvious. Okay, but I will tell you on the quiz what to use. Okay. Yeah, because this one, it's hard to know exactly what you should use, but just the proof by contradiction works pretty nicely on this one. Okay. Okay. Another good clue that you might want to use either a contrapositive or a contradiction is when your conclusion has a bunch of ors in it, because proving something or something or something is hard, but if you negate that, you get something and, where all of them have to be true at the same time. And that's much easier to work with than the ors, where only one of them, but the other ones don't have to be true. It's much easier if you know all the things that are true, rather than, well, this one may or may not be true, this one may or may not be true. It's really hard to reason about things. So here we see this or, okay, that's a good indication that we're probably going to want to negate that. So either contradiction or contrapositive are good candidates for this one. Okay. But we're going to use a proof by contradiction. Okay, so here we've got the average. We want to prove that the average of 3 real numbers is greater than or equal to at least one of the numbers. Okay, so if I were to write this out, okay, my hypothesis is just simply that I have 3 real numbers. So I'll just call them like x is a real number and y is a real number and z is a real number. Okay, so I've got 3 numbers. If I have 3 real numbers, then what can I conclude? Well, they're average, so that's x plus y plus z over 3. The average is greater than or equal to at least one of them. So is it greater than or equal to x, or that average is greater than or equal to y, or that average is greater than or equal to z. Okay, so that's what we're trying to prove there. And that's so when we have these ors, that's when you say, oh, that's a nightmare. Trying to get this to be with these ors, I have to just show that at least one of those things is true. Reasoning about that is tricky. Okay. But if I negate that, I get, okay, let's look at what is the negation of this.
Less than X and Y and Z.
Yeah, it's less than X and it's less than Y and it's less than Z. Okay. That's much easier to work with. Like if I knew that was true, then I know how the values, how the average relates. So this is true, and this is true, and this is true. That's the only way for this whole thing to be true. Easy to work with, hard to work with. Okay, so it just the way that it's written gives us an indication that we have to do something to negate that conclusion, or it's going to be a nightmare. Okay, so proof by contradiction is a good idea. So that's what we'll do. Okay. Notice, if, like, let's say, well, how do you know it's proof by contradiction instead of proof by contrapositive? So let's say we did try to do proof by contrapositive. Assuming these things are true, these have to be real numbers. Well, we haven't necessarily said what the definition of real numbers is yet. Like, we don't really know we have never done that before. So hopefully it's pretty obvious. I definitely want to negate it. I don't really know how to, like, prove that this would be true. So let's go with proof by contradiction. Okay. Okay, so we use a proof by contradiction. All right, so let X be a real number, Y be a real number, and Z be a real number. Okay. Also, so that I don't have to write this out 100 times, I'm just going to call that, okay, define A equals X plus Y plus Z over 3. That way I just don't have to keep writing that over and over and over again. Okay. All right, so remember, in a proof by contradiction, we're going to say, all right, so let's assume or suppose that the negation of the conclusion is true and see where that would take us. Okay. So let's suppose that the average of those three numbers is less than X, and the average of those three numbers is less than Y, and the average of those three numbers is less than Z. Okay. All right, so let's think about what that would mean. All right, so that means that let's go ahead and add these up. So if I add the left sides, A here, I do A plus A plus A. I'm just going to write it out that way. Okay. So if I add all the left sides, and these are all lefts than the things on the right-hand sides. So if I add up the right-hand sides, okay, since X is bigger than A, Y is bigger than A, Z is bigger than A, certainly the sum of X, Y, and Z is bigger than A plus A plus A. So that means that 3A is less than X plus Y plus Z. So A, we defined it to be like this. I'm plugged in, but I think this one doesn't actually have it. I think it's, all right, is that better? Sorry about that. Okay, so we know A is really this. Let me substitute that in there. That's 3 times X plus Y plus Z over 3 is less than X plus Y plus Z. Okay. So if we multiply it out, those cancel, and that means that X plus Y plus Z is less than X plus Y plus Z. Is that possible? No. X plus Y plus Z equals X plus Y plus Z. You can't have three numbers whose sum is less than their sum, right? This is impossible. Okay. Which is a contradiction. Okay. Well, where did that contradiction arise from? Well, it arises from following the path of, well, what would happen if A were less than X and A were less than Y and A were less than Z? So if that were true, we'd get into this impossible situation. Okay. So that couldn't have possibly been true, right? So therefore, yep. Therefore, the average has to be greater than or equal to X, or the average has to be greater than or equal to Y, or the average has to be greater than or equal to Z. And that's what we were trying to prove, that it's greater than or equal to at least one of those. At least one of these has to be true for the or of all these to be true. Proof by contradiction. Good? Fun? Hurt your brain just slightly? Okay. So, okay. Very useful. Practice those. You know, find some good ones to do. You should be able to find some good ones at the end of the book and just practice. Okay. All right. So, good review of that. You know, chances are you're going to see a proof by contradiction on Tuesday, so just practice. Okay, so the next section that we want to look at is a really brief overview of summations. I'm sure that you've covered this previously. You've seen summations before, so we don't have just going to point out a few useful things and get them back in your memory, and then we're going to start a new proof technique, proof by induction, my favorite proof technique. Okay. Sorry, this is in the way. All right, so summation, often called sigma notation. I'm sure you've seen it. I hope you've seen it. Okay, so where you have the sum of I equals S to T, and then some expression involving I, that just means that you go and you say, okay, well, I'm going to start here at S and plug that in for I. And then I'm going to move to the next integer value. These S and T have to be integers. Then I'm going to move to the next value after S. So I'd go to S plus 1 and plug that one in. And I just keep going to the next one and the next one and the next one. Okay? And then I'd stop at the end when I get up to the number that's here at the top of the summation. Okay, so there's a few different parts. Okay, this I right there is called the index of the summation. Then the lower limit of the summation is the first value that you assign to the index. So in this case it's S. You know, that's where you start. That's the index that you use when you start the summation. Then the upper limit is always listed at the top. In this case for us it's T. And then if we talk about the summation form, that's the thing on the left. That's this form, the sum from I equals S to T of A sub I. That's the summation form. The expanded form is, okay, well, what would happen if I went through every single index from S all the way up to T and just wrote out the sum in a long way? So that's this right here. So that's the A sub S plus A sub S plus 1 plus ... all the way up to like A sub T minus 1 all the way up to A sub T. Okay. So if we use those terms, the summation form, the expanded form, that's what they all mean. So let's do an example. So notice I've got my indexes I. Okay, and so that this expression in here should involve I. Okay, usually it will involve I. Okay, and then this 0, that's the index where I start my summation. 4 is the index where I stop my summation. And I need to consider every I starting at 0. So it'll go 0, 1, 2, 3, 4. And when I get to the upper limit, that's when I stop. Okay, so I start by saying, okay, well, when I is 0, I would plug a 0 in there. This would give me 2 times 0 plus 1. Okay, so that would be the value that I would get for my first index. And then I add on, and I go to the next I equals 1. Okay, when I equals 1, this is 2 times 1 plus 1. I haven't reached the other limit, so I keep going. On to I sub 2. Okay, so that would be 2 times 2 plus 1. and then I go, yeah, we'll fill them in a minute. You have all those in your mind, and then you can just whip them out when I get there. Okay, then I equals 3, that's going to be 2 times 3 plus 1. Okay. And then you're going to go on to I equals 4, so you'll add on 2 times 4 plus 1. Okay. And now I've reached my upper limit, I stop. So I sum up everything, the first, second, third, all the indices from 0 to 4. Okay, and then what were our numbers?
1, 3, 5, 7.
1, 3, 5, 7, 9. It shouldn't be surprising because 2i plus 1, that's the form of odd integers, right? So it's just adding up odd integers. Okay, and the sum of those odd integers is 10, 25. Okay. So it adds up to 25. Okay. All right, so, and you have all seen summations before, yes? Yes, yes, good. All right, good. Because if not, you're going to have to do a crash course. Okay, so some important things about summation. So when we get to doing our induction proofs, it's going to be really, really important that we know how to rewrite our summations by pulling out a final term. Okay, we'll practice. But so here, so if I have a summation that goes from I equals 1 to n of a sub I, okay, what I'd like to do is rewrite this summation by pulling off the last term and putting it separate, and then keeping the rest of the summation together. So notice I'm rewriting this as a summation plus a separate term. So I'm going to write this one out the long way so you have an idea where this came from, and then you'll visualize. So this one right here, remember if I have the summation, okay, from I equals 1 to n of a sub I, an expanded form, that would be a1 plus a2 plus a3, and on and on and on it goes, plus a sub n minus 1 plus a sub n. Okay. So if I want to rewrite this by pulling off the last term, pulling out the final term, I kind of want to cut it off right here. I want to keep this one separate, but this one I just want to go ahead and rewrite, leave that part in its summation form, right? So that's the summation. I is starting at 1, and it ends at the index right before this one that we pulled out. So it ends at n minus 1, and we're adding together all of these. Okay. So notice that's this right here. That's all we're doing. We're imagining, okay, if I expanded it out and just took the last one off, okay, I'll leave the rest of it in its summation form, but the last one I'm going to pull off. All right, let's try it here. So imagine this is all written out in this long way, and I want to pull off just the last term. Okay, so right now it starts at 0 and goes up to index n, all the way up to index n. Okay, so I'm going to pull off that nth, the one that at index n, keep it separate, and I'm going to stop my summation at n minus 1, just like we did up here. Okay, so I'm going to leave the first part of the summation starting at 0 and going up to n minus 1. Okay, that part I'm just going to leave as it is. Okay, and then I have to add on the last term. Okay, so what was the last term? Well, what was the last term is the last thing that would get added on was when k is equal to n. Okay. Well, then I'd have to substitute n into this expression. That would be the last thing that got added on. So when k was n, this last term would have been n squared plus 2n plus 1. That's the last term. Questions about that? Does that make sense? Okay. I'm just taking off the very last index and inserting it into this expression. The next one will be a little trickier. Okay. This one is pretty straightforward. All right, so imagine I had this one from k equals 0 to n plus 2 of k squared minus 2k. Okay, I just want to pull off the last term. So I start my summation at k equals 0, and then the one before n plus 2 is n plus 1. So I'm going to have to stop this summation at n plus 1. Okay. And I just leave this alone, this summation alone. Okay. And then I have to add on the last term. Well, the last term would be this expression evaluated when k is m plus 2. So that would be, well, m plus 2, that would have to be squared, minus 2 times, well, m plus 2. So I'm just taking the last index, the upper limit on this index, and substituting it into that expression. Okay, so if you were going to k equals 0 to m plus 1 of this expression, okay. And then this one, let's see, this is m squared plus 4m plus 4, and this is minus 2m minus 4. So let's see, those go away, and we could simplify this to be plus m squared plus 2m. Certainly it's easier to see when you write it out that way, but you probably want to simplify it and write it out that way. Okay. So that's, these two things are equivalent, this sum and this sum. It's just that we've pulled off the last term of that sum. So that's one thing that comes up in every induction proof involving summations, so we have to get good at that. Okay. Another thing that we want to consider being able to do is to change our variable that's being used for our index. So let's say that our index right now is j. Okay. But I know that I have this expression that I equals j plus 2. Let me write this down bigger so you can see it. Okay. And so I want to rewrite this summation in an equivalent form, but I want to use I as my index. So I want to rewrite this sum as the summation from I equals something to something of something. But everything needs to be now in terms of I instead of in terms of j. Okay. So let's say, all right, just consider, well, what would, when j is 0, okay, well, what would I be? Well, I would be equal to 0 plus 2 or 2. Okay. So starting j at 0 is equivalent to starting I at 2. All right. And then when j is n, our upper limit, well, since I is j plus 2, I would be n plus 2. Okay. So in terms of, now I know that when I write this summation out, I need to have my summation go from I equals, well, when j is 0, I is 2, so those are equivalent. And we stop when j equals n, that's the same as when I is equal to n plus 2. And now this right here, okay, so j plus 2 is actually the same thing as I. So I can replace this j plus 2 with I. And now these two are equivalent forms. Okay. So notice this would be 2 plus 3 plus 4 plus 5 plus 6 until it gets up to whatever n plus 2 is. Okay. Here, when we start at j equals 0, this one would be 0 plus 2 is 2 plus 3 plus 4. You're getting the same numbers, right? These both would generate 2 plus 3 plus 4 plus 5 plus 6. Okay. The nice thing about this one is the expression here is much easier to work with. Okay, so this is a nice way to rewrite the summation. Okay, so because of the simplicity of the expression that you're using in your summation. Okay. Let's do another example over here. Here we have I equals j minus 1. Okay. So once again, if we want to switch our summation to the summation from I equals something to something. All right, well, when j equals 0, what's I going to be? Yell it out if you know it. Negative 1. Just substitute 0 in there. All right, so that means we need to start our lower bound there at negative 1. And then here, when j is n plus 1, that's our upper limit. Okay, what will I be when j is n plus 1? Anyone? I heard it. Can say it louder? I thought I heard it. N, yes, n. Right? So just substitute n plus 1 in for j, n plus 1 minus 1 is just n, right? So this will stop at n. Okay. And now the expression here is a little bit trickier. So this one, let's solve this for j. So down here, if I equals j plus 1, then j equals I plus 1. So this expression right here, j squared would be the same as I plus 1 squared minus 2 times I plus 1 plus 1. All right, so that's I squared plus 2I plus 1. Distribute the negative 2. That's minus 2I minus 2 plus 1. Okay, so we have a 2I minus 2I. That becomes 0. 1 plus 1 is 2 minus 2. That becomes 0. And we're just left with an I squared. So once again, this expression in here is much simpler to work with than this expression over here. So it might be advantageous to rewrite our summation this way just because the expression used in our summation is simpler. Okay. All right. And before we move on to our next proof techniques, we want to talk about closed forms. So a closed form for a summation is an expression that will give you the value of the summation, but it doesn't use summation notation. Okay. And again, you probably have seen these somewhere. So for example, we talked about arithmetic sequences last time. A arithmetic series is what you get when you add up all terms in an arithmetic sequence. Okay, so a series is a summation of terms in an arithmetic sequence. Also, geometric series is the sum of terms in a geometric sequence. And these have nice closed forms. Perhaps you've encountered them before. Okay, so notice this expression right here. So you've got an initial term and you add on some multiple of a common difference. These will generate values in an arithmetic sequence. And then I would sum a whole bunch of these together. So this is just a sum of numbers in an arithmetic sequence. Okay. The formula that the Zybook gives you for this is this crazy thing right here. Okay. When I look at that one, I say, oh my goodness, how would you ever remember that? Okay. So this is equivalent to this. I like to rewrite this one this way. Okay. And this one is super easy to remember because this part right here is the average of the first and last terms. And then this is the number of terms. Okay. So you can, like if you were going to add up all the numbers in an arithmetic sequence, okay. If you took, there's n numbers in this sequence. If you just took the average of the numbers and multiplied it by n, you would get the sum. Okay. So this is a fairly intuitive formula. It's the average of the first and last term times the number of terms. This, oh my goodness, a sub 0 times n plus d. I don't even know. So I don't know how you're going to memorize that one. I would use this one. Super intuitive. Okay. I bet you want me to convince you that these two things are the same, though. So I will. I will. So let's look at this crazy thing and convince ourselves that it actually equals this. Okay, so we've got this a sub 0 times n plus d times n minus 1 times n over 2. Okay. Okay, so if I wanted to add these two things, I would like to find a common denominator. So I'll rewrite that one. Okay. And now looking at, you can kind of see here that this n over 2 got pulled out. So I've got this n over 2 factor here, and I've got this n over 2 factor here. So clearly we could factor that out. So let's take out the n over 2 factor. And we would be left with 2 a sub 0 there plus d times n minus 1 right there. Okay. So let me just rewrite this one just as a sub 0 plus a sub 0 because it'll make it easier for us to think about. Okay. So this part, if I start at a sub 0 and I add on n minus 1 common differences, okay, well, that's just the formula for how you find the n minus first term of an arithmetic series. So this is really just a sub n minus 1. Okay. Right, you just start with the first term and you add on a certain number of common differences. Okay. So there you are at the a sub n minus first term. Okay. So notice, okay, that's just like this one. It's easier and more intuitive to remember if you kind of put the two with this, though, I think. Okay. But they are indeed the same, so it's your choice. You can memorize the book formula or the one that I give you. I advise that. Okay. This one isn't too hard. Okay, that one's actually written in a nice form. So the closed form for the terms in a geometric sequence. Okay, so geometric sequence, notice it's very similar to this one again. Okay, so you start with the first term and multiply it by the common ratio. Okay, so this is just generating values in a geometric sequence, and then we're adding them all up. So it will be the first term times the common ratio to the number of terms that you have in the series minus 1 divided by the common ratio minus 1. Okay, so let's practice using these closed forms to quickly find sums. So let's say you needed to find the sum of 2 plus 5 plus 8 plus continue the pattern and then stop when you get to 32. Okay. So let's think about, all right, so 2 is clear. So what's the common difference that's being added every time?
3.
Yeah, so the common difference is 3. Okay. So we're looking at a summation, and our a sub 0 is 2. That's where we're starting. So we're adding 2 plus, okay, some number k times our common difference of 3. And we're starting at k equals 0. And then what upper bound would I have to use so that this last one would be the number 32? What k value would I have to put in there to make this 32? Yeah, because then we'd have 30 plus 2, 32. So we'd have to stop this at 10. Okay. All right. So it's definitely in this form. We've got, k equals 0 to some number of the values that are from an arithmetic sequence. Okay. So using our intuitive formula, okay, we'll look at the first term in the sequence, which is 2. Plus the last term in the sequence, which is 32. Take the average of those and then multiply it by the number of terms in the sequence. How many terms are there in this sequence? How many terms are we adding together? Gotcha.
Oh, that's not
11, because you start at 0 and go up to 10. That's 11. So that's the tricky part. So this is actually 11 terms. Okay. 0 to 10 is 11 terms. Okay. All right, so let's see. 2 plus 32 is 34 divided by 2 is 17. 17 times 11. I always tell my students, add and squish. That's 187. Whenever you multiply by 11, you just add the two numbers and squish it in between. That's how you multiply by 11. So multiplying by 11 is easy. Okay. So we quickly can get that without having to go into our calculators and add all those numbers together if we just use the closed form of the summation. Okay. this one, okay, to get from 1 to 2, I multiply by 2. I multiply by 2 to get 4. I multiply by 2 to get 8. So we can see that this one is multiplying by the same number every time. This must be a geometric sequence, okay, where our common ratio is equal to 2. So we can use this closed form for the geometric series. All right, so we're looking at the sum of numbers that are in a geometric sequence. Okay, so our a sub 0, we're starting with the number 1, and our common ratio is 2, so that would be 2 to the k. K starts at 0. And then what value of k would I have to use to get this last term 512? Two to the what is 512? Do you know your powers of 2 yet?
9.
What is it?
9.
Yes, it's 9. Okay. So 2 to the 10th is 1024. That's a good, like, anchor point to go to. And this is half of that, so it has to be 1 less than the 10. All right, good. All right, so we have to stop at 9. And so our closed form is we take the first term in the sequence, which is 1. Multiply that by the common ratio to the number of terms. How many terms? 10. We didn't get you this time. Carlos will not be fooled twice. Okay. Minus 1 over 2 minus 1. Okay. Like we said, 1024. 2 to the 10th is 1024, so that's 1024 minus 1, which is 1023, over 2 minus 1. All right, so that's just 1023. Okay. All right. So closed forms come in handy. They're very useful because you can quickly find it without having to add up all those numbers. So we like closed forms. We love closed forms. So let's say I have this summation. We saw it already once earlier. So notice this is some odd numbers, and I want to be adding up some odd numbers. So let's do a few examples. Okay. So if I did from I equals 0 to 0 of 2i plus 1. Okay, the start and the stop are the same. That would just be 2 times 0 plus 1, which equals 1. The summation is 1. If I went up to 1 instead, well, when I put 0 in, I'm going to get 1. When I put 1 in, I'm going to get the next odd number, which is 3. My sum is 4. Let's say I went from 0 to 2. Okay, again, we're adding up odd numbers. When I is 0, I'm going to get the odd number 1. When I is 1, I'm going to get the odd number 3. Then when I is 2, I'm going to get the odd number 5, and I get 9. Okay, 1, 4, 9. Let's do another one. Just one more and see if you can, maybe you already see a pattern forming. So this one would give us 1, 3, 5, and then 7. Our sum's going to be 16. Okay. These seem like very special numbers, don't they? 1, 4, 9, 16. What would you expect the next sum to be when we go up to 4? 25, right? So it seems like we're getting these perfect squares, right? So we could make a conjecture that the sum from I equals 0 to n of 2i plus 1, okay, so when n was, 0, I got 1. When n was 1, I got 4. Okay, so it's not necessarily 1 squared. Like 1 squared is 1, 2 squared is 4, 3 squared is 9. Like what formula, closed form? If I have 4 up here for n, if n is 4, I should get 25 over here. So what's my formula that I think it is? Yeah. So you take whatever n is, add 1 to it, and square that. Okay, so notice here, so if n was 0, 0 plus 1 squared is 1. Okay, it seems like that works. When n is 1, and we stop at 1 up here, 1 plus 1 is 2, 2 squared is 4. Okay, so it works for all of these. Okay, so I have a conjecture, but me showing you 4 examples is true. Does that prove it's true? What if I did another one? Would that prove it's true? No, right? So I can show you 125 examples, and I could make you feel like this has got to be right, but it's not a proof that it's true. So we actually need a proof technique that allows us to make a general argument that would say that this is always true. And that is where mathematical induction comes in. Cool proof technique. Okay, so in an inductive proof, it's a technique for proving statements that's very useful, especially about sequences. There's lots of other things, but we're going to practice a lot for sequences because it's just so natural on sequences. We'll do other things as well, though. All right, so an inductive proof has 2 components. They're both essential. You can't have one. You can't have just one of them. You have to have both of them. Okay. So the first part of the proof is called the base case. Okay. And in the base case that we establish that the theorem that we're trying to prove is true for the very first value in our sequence. Okay. So if we were having some kind of a summation and we said, the summation from j equals 0 to n. Okay. So 0 is the index where I start. That would be my base case, the starting point, okay, the smallest sequence, the smallest index in the sequence that I'm trying to prove for. Okay, so that's my base case. And then we have what's called the inductive step. Okay, so the inductive step, I prove that an implication is true. Okay, and this is the tricky part. This just proves that an implication is true. And this is usually where students get stuck, okay, because they think it proves something that it doesn't prove. So we'll talk about this, but so in the inductive step, what we do is that we establish that if the theorem is true for some arbitrary index k, then the theorem also holds at index k plus 1. So notice the if and the then. Okay. We're just saying if it were true for k, then it would also be true for k plus 1. Now, does this prove that it's true for k? No. Does it prove that it's true for k plus 1? No. It just proves the implication that if it is true for k, then it has to be true for k plus 1. It's just proving that the implication is true. Okay. So, the power of mathematical induction is when you put both of these things together. Okay, so in mathematical induction, it says, okay, if the base case is true, like n equals 1, and the inductive step is also true, then the theorem has to hold for every single integer after the base case. Let's say if it were 1. Okay, so let's write out kind of how this works so we can see what happens. All right, so let's say I'm trying to prove some predicate P of n, and I want to say that P of n is true, okay, for all values of n greater than or equal to 1. Okay, so the way that I'm going to do this with induction is I'm going to say, okay, well, what's the smallest value of n? Like, give me a starting place. Well, the smallest value of n I can think of is 1. That's my starting point. So the first thing that I do is I show that P of 1 is true. And then I say, now I'm just going to pick an arbitrary k, okay, and I'm going to show that if P of k is true, then P of k plus 1 is true. So I know that this implication is true. Okay. Now, just because the implication is true doesn't mean P of k is true. It doesn't mean P of k plus 1 is true. I could have false implies false and still have this be true, right? I just know that the implication is true. Okay. But when you take these two things and you put them together, that's when we get magic. Okay, so imagine that I've told you that P of 1 is true. Okay. And I know that this implication is true, let's say for all value, for some k. Okay. Well, if it's true for some k, okay, then it could be true for 1. So I could have that p of 1 implies p of 2. Okay. Well, if I have that this implication is true, and I know the hypothesis is true, then by modus ponens, then I can conclude that p of 2 is true. So now I know that if p of 1 is true, then p of 2 is true. P of 1 is true. So p of 2 must be true. Okay. Then I go here and I go, well, if p of 2 is true, then p of 3 is true. Well, I know p of 2 is true because p of 1 was true. So so now I get p of 3 is true. Well, this told me that if p of 3 is true, then p of 4 is true. Therefore, I get p of 4. Okay. And so I keep going on and on and on and on forever. And so now, because I have these two things, I can show that these two things together give me that it's true for every single value of n after 1. Yes?
If the inductive part was like false implies false, wouldn't that mean there's a number greater than 1 that isn't true?
And that's why it's so important that we have this starting point p of 1. Right. You are right. Okay. So if all I had was this part, it doesn't prove anything. Okay. But if I can show you that this is actually true, now that's a whole different story. Right? And that's the key. So you have to have a starting point. So if all I do is show you p of k implies p of k plus 1, who cares? So what? You haven't told me anything. Okay. But you give me this and I get this chain reaction. Okay. But without the base case, I don't get a chain reaction. And so both of those parts are absolutely important. And you can't just have this, because that's just one case, and you can't prove something with one example. And you can't just have this, because there's lots of things that make this implication true. It doesn't tell me that p of k is true. It doesn't tell me p of k plus 1 is true, just that I have a true implication. But you put them together, and you have this starting place, you can start this chain reaction, and now you can get them all to be true. Because this sets off this big long chain of modus ponens. Okay. So that is the power of induction, and we need both of them. So let's do some examples, okay, and see how it works. All right. So we want to prove, this is a very classic closed form formula for a summation. If I take the numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6, and I add from 1 up to n, okay, I can quickly evaluate that sum by doing n times n plus 1 over 2. Okay. This is attributed to the mathematician Gauss. I don't know if you've ever heard the story. So as the story goes, you know, I think a lot of those little brilliant mathematicians were naughty children in school because, you know, their minds were so active and they were bored. And so apparently all the children in Gauss's class were being naughty and the teacher was just fed up. And so he gave all the kids an exercise and he told them, you know, I want you to sit down and add up all the numbers from 1 to 100. And so all the kids are busy there adding numbers. And little, I think his name is Frederick Gauss, I can't remember, comes up 2 minutes later and tells them what the sum is. And the teacher's like, what? How did you figure that out? And Gauss explains how, he's like, well, I figured if you do 1 plus 2 plus, and you go all the way up to 100, but then let's say if I write them backwards, 100 plus 99, and I just write them backwards, down to 2 plus 1. If I look at each of these individual pairs, this is 101, this is 101, this is 101, this is 101, or they're all 101. So I took the 101, and I've got 100 of these pairs, okay, but that's twice the sum, so if I divide, so if I divide it by 2, then I'll get the actual sum, and so I just have, let's see, this is 50 times 101, and then what do you get on that? So that's 50, 50. Okay. And so he was able to quickly figure it out. And the poor teacher didn't get any piece. So notice that's kind of what's happening here too, except for going up to 100, I could go all the way up to n, okay? All of the sums would add up to n plus 1. I would have n sums, but I've double counted the sums, so if I just divide that by 2, I'll get the sum of all those numbers. It works the same way. All right, so thank you, gals, for telling us how to do that, even when you were a little genius boy. Okay, so this is course. You could actually come up with a direct proof kind of way to do this, but it's more fun to do induction. So let's do induction. Okay, so we're going to do a proof that this is actually the closed form of this summation, and every time you do the summation, this formula will give you the answer. Like, that's what we're trying to prove. Okay, so we always, if we're not using a direct proof, we alert the reader. So we use a proof by induction on n. Okay. So n is the stopping place. You know, we're saying that this is true for any positive integer n. So whatever n you're thinking about, that's what you want to do your induction on. Okay. And so think about positive integer n. That means n will start at 1. That's the first positive integer, then to 2, then to 3, okay, and on and on. So the smallest one right there, this is going to be our base case. That's going to be the starting point that we have to use to start the chain reaction. And that's the first one we're going to prove. Okay. So I'll just go ahead and label it. If you just kind of want to write these out in paragraphs, and you can. Okay. But I like to label base case and inductive step for you so you can see how the flow is going. Okay. So the base case, we know it has to be for any positive integer, so we have to start at the first positive integer, which is 1. So we'll start there. So when n equals 1, okay, we're going to look at both sides of the equality, see what this would give us, see what this would give us, and see if they are indeed equal. Okay, so when n equals 1, the left side, the summation from I equals 1 to n of I, well, if n were 1, I'd replace that n with 1. So that would be the summation I equals 1 to 1 of I. So I start at 1, substitute it into that expression, and I stop at 1. There it is. That's what it is, right there. Okay. So that's what the left-hand side of the summation is. Now let's look at the right-hand side of the equality. So let's look at the right-hand side of the equality and see what value that gives us. So if I had n times n plus 1 over 2, well, if n were 1, that would be the same thing as 1 times 1 plus 1 over 2. 2 cancels with 2. That just gives us 1. Okay. Indeed, these are both exactly the same. Okay. So the statement is true for the base case of n equals 1. Okay. So that gives us our base case. Okay. Very important, because that's the thing that's kind of going to start our chain reaction. So after we do that, the next thing is to do what we call the inductive step. Okay. So the inductive step is going to be this, well, if it's true for k, then it's got to be true for k plus 1. Okay. All right, so the inductive steps, okay, is going to say, all right, well, assume that, well, we want it to be true for k. So we're going to go up here. We'll see what we're trying to prove is true. Okay, and and then we're going to say, all right, well, if n were k, and let's replace all those with k and just assume that it's true there. Okay, so assume that the summation from I equals 1 to k of I is equal to k times k plus 1 over 2. Okay, assume that that is true for some, and this is some arbitrary k, that is in the set that we're thinking about, in the set of positive integers. Okay. So this right here this thing that we're assuming. Now I don't know if it's true. I'm just following the path. What happens if it is true? So this thing right here is called our inductive hypothesis. Okay. So notice, I'm just assuming it's true. I don't know if it's true or not. I'm just saying, let's see what would happen if it were true. So let's see, like, follow the path and what would be true if this were true. Okay, well, what we want to be true is if it's true for k, then it would be true for k plus 1. Okay, so that's what we're going to try to show. So we show that when we do this sum starting at 1 and we end at k plus 1 instead of k, so the next index after k, okay, then the formula is still going to work. So our upper bound is now k plus 1, so we put k plus 1 in for n, and we put k plus 1 in for n there. Okay, so that's our goal. So if this is true, then that is true. Okay, so we assume this is true. If that is true, we'll show this has to be true. So this would give us the implication that we need. Now, no, we don't know if this is actually true. We don't know that this is actually true. We just know that if this is true, then that will be true. Just that the implication is true. Okay. So all the power is kind of back here that gets our chain reaction started. All right, so our goal is to show that this summation is going to work out. All right, so let's explore like how we've got this summation right here. So we've got this summation from I equals 1 to k plus 1 of I. Okay. I'd like to show that it's actually that. Okay. So if I think about, well, what do I know? Well, I'm assuming that if I stop at k, okay, then I'll get this. Right now, this summation stops at k plus 1. So let's rewrite this summation by pulling off the last term so that this summation only goes to k, because I know if I stop at k, I have something that I think that that summation is equal to. So that's why we need to be able to pull off the last term. So I'm going to rewrite this as I equals 1, and I'm going to stop before k plus 1. I'm going to stop at k. Okay, well, that's not the whole summation, so I've got to add on, well, the last term that I'm missing from this one is when I was k plus 1. Okay, so that I would substitute that into this expression here, so I'm missing, I would have to add on an extra k plus 1 to that one. Okay. And now I look and I go, oh, well, I was following the path of what would happen if the sum from I equals 1 to k of I was this thing. So I'm just going to take that value right there and substitute it in for this summation. Okay. So I'm going to have this be k times k plus 1 over 2. Okay. And this is by the inductive hypothesis. So when you use that inductive hypothesis, you should make a note of that. So the only reason that this works is because I assumed that this summation and this closed form were actually the same thing. Okay. So everything I'm doing here depends on the fact that these two things are equal. Okay, so if that is true, then all this other stuff that I write down here will also be true. This is where I'm getting this, why I'm getting an implication that's true. If this is true, then whatever I say next has to be true. Okay. All right, so now I want to have a kind of a closed, a nice, single fraction. So let's do a little bit of algebra on this. So this would be, let's just go ahead and distribute the k. This would be k squared plus k. Okay. A common denominator of 2. I'd have to multiply this one by 2 over 2. So this would turn into 2k plus 2. Okay. I'm going to need to go that direction instead of down because I'm running out of paper. But this is k squared plus 3k plus 2 over 2. And if you factor that, okay, then you get k plus 1 times k plus 2, right? And that's what I was hoping it would be. So I have right here that the summation from I to k plus 1 of I is actually equal to k plus 1 times k plus 2 over 2. Okay, so I've shown what I set out to show. Okay. Now the important part is this is only true if that's true, if that substitution that I made there is true. So I've just proved an implication. If it's true for k, then it's true for k plus 1. Okay. And so then I would end up by saying, therefore, by the principle of mathematical induction, which from now on I'm going to abbreviate as principle of mathematical induction so that I don't have to write out so many words.
Okay.
Yeah, POMI. Therefore, by the principle of mathematical induction, I know that this has to work for every single value of n, 1 and greater. Okay. So that's what mathematical induction tells us. This is going to start a chain reaction. This, along with this, starts a chain reaction, and it'll be true for every value after, n equals 1. Now, we've said nothing about n equals 0. We've said nothing about n equals, like if the n is anything else, it has to be 1 or bigger. Okay, so that this formula works, okay, for all values of n that are positive integers. Okay, so 1 and greater. Make sense? Maybe? Yes? Kind of? We should probably do more, right? Yeah, let's do more. Do we have time? Yeah, we have time for this one. Okay, this will be our last one. Okay. Oh, yeah, this is another easy one. The next ones are hard anyway, so. Okay. All right. All right, we've kind of got it down now. Let's try again. All right, so once again, I've got a closed form. Any positive integer n, I want to say, all right, if I were to start j at the index of 1 and go up to any positive integer n, okay, of 2, or j times 2 to the j, I'm always going to get that's n minus 1 times 2 to the n plus 1 plus 2. Okay. Wouldn't you like to meet the person that figured that out? Okay, so, but we're going to prove it. Okay. Okay, all right, so the proof is by induction on n. I might abbreviate some words for time. Okay, so we have our base case. Okay, so we think about the positive integers. Got to go to the very first one. Okay, the smallest positive integer is 1, so we got to start there. That's got to be our base case. So we start there when n equals 1. Okay, let's look at both sides of this equality, evaluate what the expressions would be, and see if they're equal. All right, so we've got the sum from j equals 1 to n of j times 2 to the j. Well, if n is 1, let's substitute 1 in there. All right, so we start here at 1. That will be 1 times 2 to the 1. And we stop when we get to 1, we're already there. Okay, so this is just 2. So that's the left side of the equality. The right side of the equality, the n minus 1 times 2 to the n plus 1 plus 2. Okay. Well, if n were 1 and we substitute that in there, we'd get 1 minus 1 times 2 to the 1 plus 2. Well, this is 0, so this whole part goes away, and we're just left with 2. So indeed, these values are equal. Okay, so thus the statement is true for our base case of n equals 1. Okay, that's our anchor point. That's the none of this works without that base case. Okay, then we're going to look at the inductive step. Okay. So now we're just going to say, all right, well, I'm not going to consider every possible n. I'm just going to pick some arbitrary n. Okay, I'm just going to call it k. All right, so we're just going to assume that that summation from j equals 1 to k of j times 2 to the j is actually equal to k minus 1 times 2 to the k plus 1 plus 2 for some positive integer k. And now we say what we want to show is if it's true for k, then it's going to be true for k plus 1. So we have that implication. Now we don't know that it's actually true for k. We just say if it is, then it'll have to be true for k plus 1. All right, so we're going to show that when I take my summation and I stop it at k plus 1 instead, that the formula still works. So if I substitute k plus 1 in there, so k plus 1 minus 1, that's k, times 2 to the k plus 1 plus 1, okay, that's k plus 2 plus 2. So we just want to show that the formula still works, okay, for k plus, if it works for k, then it's going to work for k plus 1 as well. Okay. All right, so let's look at this and see if we can figure out what it's equal to. So we have the j equals, our j from 1 to k plus 1 of j times 2 to the j. Okay. Now all of this is dependent on this assumption that we make. So we made an assumption that we have an expression for the sum of j equals 1 to k. Okay. So it's very important that we split this apart so that we can use this assumption. So we're going to split this apart and stop this summation at k instead of k plus 1 so that we can use this assumption that we made up here. All right, well, we stopped short, and so we need to make sure that we add on that last final term. So the final term was when j was equal k plus 1. So we put that into this expression. So what we still need to add on to this to make sure that it's still equal is k plus 1 times 2 to the k plus 1. So now if we go back here, this is our inductive hypothesis. And we say, okay, well, I think I know what the closed form of that is. So I can take this right side and replace it for this summation. So I'm going to replace that summation with k minus 1 times 2 to the k plus 1 plus 2. And then, of course, I got to keep the rest of it as k plus 1 times 2 to the k plus 1. Okay. And the only reason that we can make that substitution is because we assume that this inductive hypothesis is true. We're using the inductive hypothesis, so we should make a note of this. This is by the inductive hypothesis. Okay. All right, and then it's just a matter of algebra. Okay. So our goal is to get it to look like this. Okay, it's going to have this little loose plus 2 on the end of it, which it already has. That's nice. Okay, and then there's going to be this other, k times 2 to the k plus 1. Okay, so we might want to think about this 2 and these two terms, kind of like, hopefully this 2 is going to be that, and the rest of this stuff is going to turn into that. So what I see is I've got this common factor of 2 to the k plus 1. Okay. So let's factor that 2 to the k plus 1 out of these two and rewrite that, and then just let that little plus 2 be on the end by itself. Okay. So I've got this 2 to the k plus 1. So when I factor it out of this, I'll have k minus 1. And then when I factor it out of this, it'll be plus k plus 2. Sorry, plus k plus 1. Okay, so that expression right there takes care of these two terms, and I still need to add the plus 2 at the end. Okay, so if I just rewrite this expression, I've got 2 to the k plus 1. Well, minus 1 plus 1, those go away. This is just 2k. Okay, so there's my k. I see that. And what's 2 to the k plus 1 times 2? Think of that as 2 to the first. If I have 2 to a power times 2 to a power, what do I do with the exponents? Add them, right, okay. So think of this as being 2 to the first, so when I multiply 2 to the k plus 1 times 2 to the 1, I just add their exponents, and I get 2 to the k plus 2. Okay, so plus 2, and voila, that's exactly what I wanted. I now show that that summation is equal to k times 2 to the k plus 1 plus 2. Okay, so if this were true, then this one would be true. Okay, so our base case together with our inductive step, so we say therefore by the PAMI, by the principle of mathematical induction, okay, this formula is equals this, okay, for all n that are positive integers. Because I started at the first positive integer, and this allows me to get to every other positive integer after that. Is mathematical induction not like the coolest thing ever? No? Yes?
I don't know how to describe how I feel about it. It just makes sense. Like it just.
Yes, it's just cool. Okay, and so do you feel the recursive nature of it? Yeah, so if you have a recursive algorithm and you're trying to prove what some recursive algorithm does, you got to use induction. Okay, you've got your base case, you've got your recursive rule, you know, it's got recursion written all over it.
We're not parsing this now. It says $0.